Niels Sloane, the president and founder of the OEIS Foundation, and we are very happy that currently also the hopefully permanent visitor at Rutgers University. And Neil will talk about very interesting stuff, 2178 and all that. Also, by pure coincidence, it happens to be Neil's birthday today. Even though he's a local guy, because it's his birthday, we're going to take him out for dinner. And at the Evelyn restaurant, the usual place, 6:45. Everybody is welcome to join us, but please let me know immediately after the talk.
Thank you, Duran. Maybe we should turn off the show. Is it this one? Until I leave the board. So I should explain the title. If you ever studied English history, you know that the sequence of English kings is very confusing. For instance, starting in 924, the kings were Alfred, Athelstan, Edmund, Edred, Edwig, Edward the Peaceful, Edward the Martyr, and Athelred the Unready. And these are very confusing names and very hard to memorize. And in the 1930s, Punch did a series of parodies of English history, which later became collected in a book, which I meant to bring. It's called 1066 and all that. And there it is. This is the original English version. It's been reprinted with a different cover, perhaps more appropriate for modern audiences. But this is the referring to the not the Magna Carta, but the Magna Garta. And that was in 1930. And so I was going to call my talk. So they had a series of test papers in this book, in these articles in Punch. This is English humor. Give the dates of at least two of the following: William the Conqueror in 1066. And what is a Plantagenet? Do you agree? Trace the bosom of the Pope. Estimate the size of little Arthur. And at the bottom, the seventh question: King John had no redeeming features. Illustrate. The last one is arranged in this order: Henry the First, Henry the Second, Henry the Third. Do not attempt to answer this one. So I was going to call my talk 1078 and all that, but 1089 and all that. But unfortunately, there was a book which came out in 2002 with that title, so I had to change it. And this is a book of little amusing stories about mathematics aimed at the general public. And the reason the first paragraph is about 1089, but it's talking about a different 1089 that I'm going to be talking about. Their 1089 it has the property that if you take any three-digit number, for instance 781, reverse the digits, subtract, reverse the digits and add, you always get 1089. But my 1089 is different. My 1089 and its companion 2178 have the property that, this is very ancient, that if you multiply 1089 by 9, let's do it, 9 9s are 81, so 1 with 8 to carry. Normally you don't write down the carry digits, you're supposed to remember them, but in this situation, it's good to write down the carry digits. So 9 8s, 72 plus 8 is 80, 0, 8 to carry, 9 and 0s plus 8 is 8, and 9 1s are 9. And what you end up with is 9801, which is the reverse of what you started with. And likewise, 2178, if you multiply it by 4, you get 8712. And in the famous book by Ball and Coxeter called Mathematical Recreations and Essays, they mention this fact. These are the only two four-digit numbers with this property, and there are no smaller examples. That was 1939, their book came out. And then the following year, G.H. Hardy wrote his Mathematician's Apology. And in there he said, he was talking about what's what are interesting mathematics and what isn't. He said this. He mentioned this fact and said this is of no interest. It's likely to amuse amateurs, he said, but it's not of interest to mathematicians, since the result is not capable of any significant generalization. Well, he was wrong. Because even going back to 1908, there are generalizations mentioned in the Intermedia de Mathematicians. And after Hardy's book came out, there wasn't much mention of it until 1966, when Alan Sutcliffe wrote a nice paper about this in Mathematics magazine, followed by a paper he left a couple of questions. Oh, in fact, he left a lot of questions unanswered. And Ted Kaczynski, who's better known for other work, solved one of these questions. And there was another paper by Sklensky and Slomarski the next year. And then in 1992, there were two really interesting papers by Anne Ludington Young in the Fibonacci Quarterly, and Lara Pudwell from this seminar wrote about this in 2007. It's very hard to find out who's worked on this problem, but because of Hardy's negative comments, none of this is mentioned in math reviews. So in this talk, I'm going to define what I mean in general by a reverse multiple, and I'll talk about the Young graphs. I'll discuss generalizations of the base 10 one, and then I'll talk about several particular families of these graphs and some of their properties. So, to give the definition, G is going to be the base, K is the multiplier, and we say that a number is a GK reverse multiple if, when you multiply it by K in base G, it reverses the digits of the number. So 1089 is a 10.9 reverse multiple, and 2178 is a 10.4 reverse multiple. And another simple example, the smallest example of length 2, if you double 8, you get 16, right? And 8 is 1 in base 5 is 1, 3. It's 13 in base 5, and 16 is 31 in base 5. So if you double 1, 3, you get 3, 1. So 8 is a 5, 2 reverse multiple. Now, I got interested in this because one of my old rock climbing partners, Selma Rosenthal, found in an old mathematics, a German mathematics book from 1943, she found the same statement of fact about the two 4-digit numbers in base 10. So she persuaded her son Gregory to work out how many there were of length 5. We knew that there were none of length 1, 2, and 3, so he worked out that there were 2 of length 5, 2 of length 6, 2 of length 7, 4 of length 8, and 4 of length 9. And she said, I know you collect sequences, here's a sequence for you. How does it extend? And I thought, well, all right, this is a challenge. So I looked into it, and just to give away the answer, these are doubles of Fibonacci numbers. So this is really 1, 2, I'm sorry, you divide by 2, and you repeat each number. So it's 1, 1, 2, and then we get 6, 6, and so on, you'll see. And the way to handle this problem is by looking at what I call Young graphs. And these are directed graphs with some nice properties, and I'll give the definition in a minute. But just to give you a hint, here's the Young graph for the question base 10 multiplied by 9. We know that 1089 is the smallest example, and you can see that here. If you follow the path from the starting node at the top to this red node, you go 1089. And if you go around this loop, you get 10989, which is another example. And this diagram contains all the information about 10.9 reverse multiples. The 10.4 graph actually looks the same, except the labels are different. They're isomorphic Young graphs. The example of base 5 that I mentioned is described by this Young graph, and here are a couple of others just to show you that these can get quite interesting. So this is the graph for 8. Base 8 multiplying by 5, base 40 multiplying by 13. And the red nodes are the pivot nodes. Well, what does that mean? So the way we construct these graphs is we start off and just write down the properties of the numbers. So suppose we have a reverse multiple. Let's call it a n minus 1, a n minus 2, down to a naught, base g. So the little subscript at the end means the base. So suppose n has the property that when you multiply it by k, we get the reverse of what we started with. So you write down what the equations have to be for this to happen. So k times a naught has to be a n minus 1 plus some carry. And the carry digits are labeled r naught r1 up to rn minus 2. I'm using the same notation that Anne Young used, so that you can compare what I'm doing with what she did. So you get, if you have an n-digit number, you get...
Oh, this is any Young, not the level n alpha Young.
This is any n.
No, the Young is n Young. Not the level n.
No, absolutely. No, this is Anne Ludington Young.
Okay.
She has 2 papers in the Fibonacci Quarterly
Okay.
in 1992. No, I don't suppose there's any relation. Famous. Anyway, if you have an n-digit number, you get n equations. So she said, all right, the obvious thing to do is to combine them in pairs. So if you take the first equation and the last equation, they have a naught and a n minus 1 in common. And so you write them down side by side like that. And you collect n over 2 pairs of equations. And you simply solve them recursively. You start off, you don't know anything, other than that the number has to end in a non-zero digit, and it has to begin with a non-zero digit. Obviously, a naught can't be naught, because then k times n would be smaller than n, and we require that the numbers get bigger. So I assume that the multiplier k is bigger than 1, so the numbers strictly increase when you multiply by k. So we solve these equations recursively. We assume that we know a naught up to a n minus 1 and a n minus 1 up to a n minus 1. We know the 2 ends of the a sequence, and we try to find the next pair of a's and the next pair of r's. We do this recursively. And in fact, there's a shortcut for doing this. You just search directly for pairs that satisfy these 2 equations. Then you can work out, in terms of the 2 a's, what the next 2 carry digits are. And you gradually build up a lot of knowledge about the possible solutions. Now, Anne Young described these by means of trees. Her trees are potentially infinite trees. But I prefer to do it in terms of a directed graph with a finite number of nodes. So in this situation, when we have solved that pair of equations, I represent it in the graph by a pair of nodes. The node labels are the carry digits, and the edge labels are the digits in the number. So when I have an edge like this, it means that in the tree or the graph of solutions, we've gone from there to there. Now, there's one technicality that we have to worry about. Because we can't end the number with 0, or begin the number with 0, the starting node has to be treated in a different way. So there'll be a special starting node. And if you follow through the steps in that argument, you end up with the following theorem: that there's a one-to-one correspondence between reverse multiples with an even number of digits and paths from the starting node to a node with a repeated pair of labels. So a node labeled RR. I don't know if you can see this. So here's here is the 10, 9 graph. This is the 10, 9 young graph. And here's the starting node, which I always represent by double square brackets. And the theorem says if you have a node with repeated labels, so for instance A to 8, if you take a path from the starting node to this node, which we call a pivot node, and then turn around and go back to the starting node, that gives us a reverse multiple with an even number of digits, in this case 1. We follow the path from the starting node to the pivot, going 1, 0. The pivot, we turn around and we go back reading the right-hand labels. So 1, 0, 8, 9, and we end up back here, and we've got a reverse multiple of length 4. And there are actually 2 nodes that have identical labels. It's 8, 8, and 0, 0. There are 2 pivot nodes. And paths that go from here to here and return, or paths that go from here to here and return, possibly going around this loop many times, gives us all the reverse multiples with an even number of digits. And the reverse multiples with an odd number of digits correspond to paths from the starting node to a pair of nodes R prime R joined R prime, where R prime may or may not be equal to each other. And these are the odd pivot nodes. When you do this, the theorem says if there are no such paths, then there are no GK reverse multiples. So here are the 2 examples again. So the red nodes are the pivot nodes. That's where you stop the path and turn around and go back to the beginning. If it's an odd length path, so you could go from there to there to there, around here and go back, that would give you the number 2, 1, 9, 7, 8.
So you can go many times?
You can go around as many times as you want, and you can go around the whole circuit as often as you want.
So there are infinitely many?
There are infinitely many, yes. But you have to stop at one of the red nodes, one of the pivot nodes. And then when you stop, you must retrace your path exactly back to the starting node. And when you're going outwards, you read the left-hand edge label each time till you get to the pivot node. And when you're retracing your steps, you read the right-hand pivot node. The right-hand edge label until you get back to the beginning. So for instance, here, if we go from this red node is a pivot node, so we could go simply 1 and then 3 back. And that's the number 1, 3, 8 and base 5 that I started off. Or we could go 1, 3, 0, 1, 3 and end up there. So we just follow all the paths and we have all, the theorem says, we get all the reverse multiples in this way. Now, in order to find out how many there are, we can simply use the standard transfer matrix method. So we look at the adjacency matrix in this graph. So I put a little sketch of the graph. I've labeled the nodes. There are actually 5 nodes, and I've labeled them 0, 1, 2, 3, 4. I look at the adjacency matrix for the graph. So 0, the starting node, is connected to node 2, and I fill in that entry with x squared. The reason it's x squared and not x is that we traverse every edge twice for an even path. So the adjacency matrix A has an entry x squared for every directed edge between 2 nodes, and zeros otherwise. And then I look at because I want to count paths of any length, I look at this matrix, A plus its square plus its cube, and so on. And then, for instance, a typical entry in A squared tells you how many paths there are. This gives you paths of length 2. This would give paths of length 4 and 6, and so on. So A times 1 minus A inverse. And now the theorem says if we want to know how many reverse multiples of the even length there are, we look at the sum of the entries of B over all pivot nodes. We want to know how many ways are there to go from the starting node to an even pivot node and then back to the beginning. Well, that's the sum of the 0th entry. So in this example, it's B01 plus B03, and you work it out. Maple will quickly tell you that the answer is x to the 4th over 1 minus x squared minus x to the 4th, whose coefficients are Fibonacci numbers. That's for the even paths. For the odd paths, the difference between an even path and an odd path is that at some point you've gone around a loop once, or you've gone between a pair of nodes. We haven't seen an example of that yet, but the generating function for odd length paths has an extra edge, an extra x in front, corresponding to the extra edge that you get in an odd length path. So you sum over all odd pivots I, the entry B naught I. And if you do that for that graph, you get the same thing with an extra x in front. So when you add two together, we have x to the 4th over that. Now we have x to the 5th. So the sum for all reverse multiples is x to the 4th plus x to the 5th over 1 minus x squared minus x to the 4th. So again, Fibonacci numbers. If we are also interested in the multiplier 4 instead of 9, the graph is the same. They're isomorphic graphs. So we get the same generating function. So when you add the two together, you get twice the coefficients of twice the Fibonacci numbers. So I don't think anyone ever observed this before. This might even have impressed Hardy, though I doubt it. But that's the extension of the sequence.
It should have impressed Hardy.
It may have not have done. Now, why Fibonacci numbers? Why do they come in? So let me explain a bit more about what these numbers are. So there are several different ways to attack these graphs. In some cases, we can actually work out what the reverse multiples are by following the paths through the graph. So let me show you in this graph here. I want to enumerate all the paths in this graph that start at the starting node, go round and round and round, and come to a red node, and then reverse themselves and go back to the beginning. Well, if we go to the smallest example is 1089, which I will call W4, 1089 at the top there. But if we decide to go around this loop a few times before we go back, that puts 9s in the middle of the number. So we get numbers like, instead of 1089, we get 10989, 109989, and so on, with any number of 9s in the middle. So I call that sequence of numbers W4, W5, W6, and so on, the subscript being the length. On the other hand, if we decide to keep going and end up at the second pivot node, what we get is 1089, 1089. And we can get, in fact, we can get any word, we can get any word that's made up of combinations of the W's together with 0. We can get extra zeros by going around this loop an extra number of times puts in zeros. So by examining the graph, we can deduce that all the reverse multiples in this case are strings that you can make by building up words out of the alphabet of 0 and then any of the W's. So now we know what the reverse multiples are. But now we observe that these are all multiples of 99. 1089 happens to be 99 times 11. W5 is 99 times 111. W6 is 99 times 1111. We could also have, for instance, W4 followed by W4. If you divide that by 99, you get 110011. Whenever you divide by 99, what you get is a number of so all the reverse multiples are 99 times a typical number which I call beta, or beta, which is a number which when you write it in base 10 has only zeros and ones. So beta stands for binary. It's a base 10 number, it has only binary digits, it's palindromic, and it doesn't contain any singleton zeros or ones. So many things are forbidden, but in particular 010 is forbidden and 101. Now it's not difficult to work out how many palindromic binary numbers there are of length n that have this property, that they never have singletons, ones or zeros in them. And the generating function is x to the fourth over 1 minus x squared minus x to the fourth, which is exactly what we started with. So this proves that these numbers are in fact legitimate reverse multiples, and because we know the generating function, we know we found them all. So this is the case for base 10, a multiplier 9, and 4. What about other cases? Well, so I programmed up the algorithm, and I produced the graphs, all these young graphs, for all multipliers and all bases up to 100. And there are a lot of very interesting and complicated graphs. And many times, this is the graph that appears. So I call this particular graph the 1089. It's the most common. This is the 1089 young graph. It's the most common of all the young graphs. And it occurs, so I made a list of when we get this graph. So for instance, in base 12, in base 17, for example, it appeared to happen for multiplier 11. But it turned out, even though that graph has the same number of nodes and edges as that, it's actually a different graph. And so, as a result of all this, it seems obvious, an experimental observation, that this graph appears as the young graph if and only if k plus 1 divides g. If the multiplier plus 1 divides the base, that's a necessary and sufficient condition for this graph to occur. Unfortunately, I haven't been able to prove that. But if it is true, then I can tell you exactly what the reverse multiples are. The young graph looks like this. This is the case where k plus 1 divides g. We assume that's true, and we assume that it is this graph. Then you can prove that the reverse multiples, the graph looks like this, because the reverse multiples are gamma times beta, where gamma, well, it was 99 in one case, which was actually 099, and in the 10.4 case, it was 198. But in general, it's t minus 1, g minus 1, kt, where t is this quotient, and beta is a palindromic number, just as it was in that case. It's got digits 0 and 1, and there are no singleton 1s or 2s. And it's an open conjecture. I must confess failure about proving this. And there's a second conjecture, which we'll need in a moment. This number, 1089, has the property that 1 plus 9 is equal to 10, which is the base. As far as I can tell, the only time you have a reverse multiple where the sum of the first digit and the last digit is equal to the base is when it's this graph. So you can prove that it's never bigger than the base. It's easy to prove from the equations that A0, if you have a reverse multiple, then the sum of the first digit and the last digit is at most the base, g. And it appears that it's equal to the base if and only if k plus 1 divides g. And half of this I can prove, but not Now, another